which is a proof-of-stake distributed ledger, and its main feature is sharding. This is some joint work with Emmanuel Ansom and Romaric Ludinard. I'm a PhD student from ART SystemX, and I'm part of the BART research initiative. We cover a lot of research topics related to blockchain. So first, I'm going to explain what we've done with Stakecube, its model and properties. Then I will describe the few building blocks that we use to construct it. And then I will go on and describe the protocol and conclude with some future work. So Stakecube is a shared ledger. This is motivated by a use case where we want to be efficient as possible. And so this is the point of sharding. And we follow a pair block agreement approach. We have a final block, one after another, no forks, and we are in the standard UTXO model. So we have a stake-bounded weakly dynamic adversary. So in the proof-of-stake spirit, the amount of the proportion of stake owned by the adversary is bounded, and the adversary can corrupt nodes. So the adversary here is Byzantine, trying to break the protocol. It can corrupt nodes and dynamic corrupt new nodes, but not too quickly. And since we are relying on building blocks, you can see this protocol as a reduction, because the actual threshold and the synchrony hypothesis are completely offloaded to the building blocks. But typically it will be 1/3 of malicious stake and an eventual synchrony assumption. And finally, we are probabilistic, but in the cryptographic sense. That is, we have a security parameter that is given, and the probability of a failure has to decrease exponentially with our security parameter. So what are our properties? So the two first are fairly standard. It's just that it's a typical distributed ledger. The blockchain of honest users are a prefix of one another, and when we add a transaction, it eventually gets added. But the more interesting properties are scalability and efficiency. So here, by scalability, we mean that the communication cost is small. So asymptotically, it's linear in the number of participants. However, there are some constants in the formula, and those constants depend on the security parameter. This is due to the committee approach that we have, because they are taken randomly. To put that in perspective, we have a solution like Durand, which have a similar communication cost, because they have this big committee. So the formula looks the same, and they have this big constant because they need a big committee to run the protocol. Here we try to reach a middle ground where we have, due to sharding, we have multiple committees, but they are small. And then efficiency essentially means that we're going to confirm new transactions quickly. So what are our ingredients? First, standard cryptographic primitive. We use also VRF, which are like a hash function, except that you get a certificate of the randomness of the output. Within shards, we use vector consensus and random beacon. Those are Byzantine-Torian protocols, and vector consensus is just a variant of a regular consensus where we get a vector of output instead of agreeing on one value. And the random beacon allows us to get a random seed, a common random seed on demand. And then we have a verifiable Byzantine agreement, but it's less building blocks than a blueprint for the actual block production procedure. We'll see that later. But the most important building block is Stakecube. It's the basis of our sharding mechanism. So basically, PeerCubes assume that nodes have a random, short-lived and verifiable identifiers and gives you the shards. If you remember Emmanuel's talk, the actual shard is made the same way that the blocks are split in Sycamore. So, but this is we won't go into the details here. What we have to remember is that each shard is divided into two random sets: the core set, which is essentially the committee that does everything, and the spare set, which is passive and follows the committee. The core set, sorry. And the nice property about PeerCube is that we get some notion of security against Byzantine adversary because all the malicious nodes are spread into all the shards. And so we say that a shard is corrupt when there are too many malicious nodes within the core set. And the actual probability of having any core set, any shard corrupt, decreases exponentially with the core size. So we can parameterize the core size with the security parameter to ensure that shards are not corrupt. And to not increase too much the size of the core set, we actually tolerate a few corrupt shards up to F, which is a parameter. So I will describe roughly the protocol execution. So first, we have that there is a random seed within each block header. This is used to bootstrap a global credential system, and this allows us to properly run a PeerCube and get our shards. And then we have that not all UTXO owners want to participate into the protocol. Some want to join and leave over time. So we have to update the shard composition. So this is done in parallel within all shards. And when this is done, we actually create the new blocks using a subset of shards, which actually produce the block. And we use the fact there is a low number of corrupted shards, typically maybe 2 or 3, depending on the constant that we use. And this is to get an efficient overall procedure. How do we build the credential system? It's fairly simple, given that we already have we build on the random seed with each block. So what we have to remember is that each credential is indexed by block height, and we get a credential T blocks after the UTXO has been included in the block, and then after that, every T blocks our credential is renewed. So here the H0 is the height at which the UTXO has been included. And then the index of the seed that is used to derive the credential is changed every T blocks. So that way we get a sequence of random identifiers which are suitable for PeerCube. So given that we have shards now, with the core set and the spare set, how do we update the composition over time? First, we have that join requests are for a specific shard and are routed directly to that shard, and the core member between blocks locally store the pending join request. And when we receive a new block, we want to go to the next composition, the next view. And so what we do is that first we remove the credentials that expire, of course, and then we run the vector agreement, which is with each buffer as input, and the union of that is a set of new spare. Then we run a random beacon to get a random seed so that we can make the correlation. So the spare member are taken to fill the core set. The core set is of fixed size, so the ones that are left are filled with the newcomers, the spare set, sorry. And then When this is done, we send the new view to only the core to all the other shards. So now that we have that, we want to actually create a block. So what we do is that we take a random subset of shards, and this subset of shards will run the Byzantine agreement to produce a block. So roughly speaking, we have some kind of leader-based protocol, but it is adapted to the setting where we have shards instead of nodes participating. And blocks are proposed by shards, and to do that, they have to actually generate the block. And they do this by doing a procedure similar to the one we do to update the composition of shards, which is we run the vector consensus to get the final list of transactions that will be included in the block. And we do a slightly different thing for the randomness, which will be the randomness associated to the block. We again run the vector consensus with the VRF output of each core member as input. And this allows us to get an agreed, to derive, not directly, but we derive an agreed random seed. And that's how a block is proposed, and if the algorithm goes well, it may be included into it may be the next one included. For future work, we plan on, we have a lot of possible efficiency improvement, including signature aggregation, like Yannick, I'm sure convinced you this morning. We actually want to extend the sharding mechanism into storage, because currently we store all transactions, but we plan on we have the right setting to make that easier. And there are a lot of security improvement, because since the efficiency is directly tied to the security, the parameterization, better theoretical analysis gives us better efficiency. And then finally, we are currently ongoing an implementation. And that's it. Thank you.
Thank you. One question in 20 seconds. What's a verifiable identifier? Like
verifiable just means that when I claim I have this identifier, I can convince anybody else in the system that I actually own it. So it's pretty much a signatures, but it's just to account to the fact that not everybody has the same view on the system all the time.
Does it fight against the Sybil attacks? Or
not really. It's already an input. I didn't say it, but we currently assume that UTXO have a bounded amount of stake within each UTXO, so there is a bounded number of malicious UTXO, but this is more theoretical simplification that we will remove in the future.
Okay, thank you very much. The microphone.